Okay. First, we're going to talk about chapter 21. So, chapter 21 is called the paired test. It's a t-test, so we know it's going to deal with means. The big question is, what does pairing mean? Well, pairing is when you take two data sets and you compare them in some way. Why is this not? Go on. So we pair two data sets. So in essence, we're taking a two-sample t-test and we're reducing it to a one sample, which has easier equations. That's the point of it. You cannot always pair data. There has to be what we call a natural pairing. Some examples are like, so you need each group. So let me just draw you a picture. Like, let's say we're comparing like the heights of men and women. So we have some data. Let's just say this is inches. We have some data sets, and then we make a new data set called the difference. And maybe we indicate it's men minus women. Then we have a new data set. Let's reverse it. There can be negative numbers in this data set. And we're only looking at this data set. So we've reduced a two-sample case to a one-sample hypothesis test. Some common pairing can be one person at 2 points in time. Maybe you wait a year, like for weighing someone or something. Husbands and wives, a cat and dog within the same household, two trees in the same forest, stuff like that. It needs to be the same assignment for everyone, something very clear, like, the same person 2 points in time. Pairings are not always possible. It really depends. Like the example I give is like, if you want to compare the mean weight of dogs and the mean weight of like toasters, like there's no way to really pair that. So you cannot always pair means, pair t-tests, I should say. But when you can, you may as well do it because it makes the equations easier. We saw how nasty the two sample t-test equations are, right? But the one sample are easy. So I'll just do the table. So our null hypothesis is that the mean of the differences, usually just say mu sub d, is equal to delta naught, which is usually 0, but not always. And then the alternative is just, it's less than, greater than, or not equal to delta naught. So we're completely forgetting about the original data set. Maybe we weren't even given the original. We were just given the difference data set. And we're going to do just basically, it's going to be almost the exact same thing as a one sample. The conditions are a little different. So the conditions are paired data, which is just data are paired, which is dependent on the context of the question. You have your independence assumption, which is also your randomization condition. And you have your nearly normal. This is histogram of differences, though. It doesn't matter if the histogram of each of the two groups are nearly normal per se, just that the histogram of the differences are nearly normal. So basically the only change is that there's this paired data condition, which is not always the case, but it really depends on the context. And then the standard error in the book, they use D bar instead of X bar, which I'll just use it. Is just standard deviation of the differences over square root n. And the T score with, I'll get to the degrees of freedom in a second, is our D bar minus delta naught over the standard error. These equations all look familiar, right? These are just the one sample with just slightly different notation. S over square root n, X bar minus delta naught over standard error. Same equations. Degrees of freedom is still n minus 1. Because you have to have two data lists of the same size in order to do a pairing. So I guess I forgot the parameters. You have your sample size, you have your D bar, your difference of the means, and you have your standard deviation of the differences. But the entire point of this is that it's just, you're taking a 2 sample and you're reducing it to a 1 sample because you have a pairing. So the equations and the math, all that works out the same as it did in like chapter 18. Any questions so far? If you need to do a confidence interval, the formula is exactly what you expect it is. It's D bar plus minus your T critical and minus 1 degrees of freedom times the standard error. And N is the number of pairs, which is essentially your sample size. Well, it is. So each of your 2 data lists have to have the same sample size. Any questions so far? Okay. One thing that's good about this, there's a subsection in your book, it's 21.4, blocking. Remember from chapter, I believe it was 11, we talked about blocking. Just we're reducing variability by doing this pairing. So we're reducing variability. So that's the other thing that's good about that it's good for. Yeah.
What is the equation about this side?
D bar plus minus T critical with n minus 1 degrees of freedom times the standard error of D bar. Right, just your standard confidence interval for a mean, one sample mean.
But what does it say next to this profile?
Standard error
Well,
of D bar. N minus 1.
Oh, I remember one.
Yeah. Or just, this could just be degrees of freedom, whatever. Yeah. But yeah, it also does reduce variability, which is good. And independence in this context means that each pair is independent of a different pair. So the 2 people might not be independent. A brother and sister are not going to be independent if we're talking about anything genetic. But as long as you're not comparing one pair of brother and sister, like let's say someone has 4 kids, 2 boys, 2 girls. You can't compare those 2 sets of boys and girls. You have to do a boy and girl in one family, a boy and girl another family, so on. But that's what we mean by independent. Each pairing is independent of another pairing. There's something I want to show you guys. Oh. Where is it? questions so far? I got one page too far. All right, this. Wait, this is a picture. This one. So you might see something like this on your test. In several different contexts. What I want you guys to notice is what each thing means. So you might see something like this. But the data, you should know that this is your sample size. You have your X bar, your S, your SE. And from here, you could fully make, your confidence interval comes immediately. For the paired means would be 2.235, this number, plus minus whatever your T critical is with 169 degrees of freedom, times this standard error, which is 0.31255. And you can use this and immediately get all your information. What is the p-value for the hypothesis test? Anyone see it? You see where the p-value is? It's over here. So this did the whole hypothesis test on a computer. Here's your T score, your T statistic. It's a different color. Your T statistic is 7.15. Your p-value is super small. This did all the math for you. What you guys might be responsible for is just saying the hypotheses, writing the assumptions. And then you don't have to do the math again. You just say the T value is 7.15, P value is super small, reject the null hypothesis. You guys see that? Actually, it wrote this confidence interval here too. So you don't have to do it. So if you see a table like this, you don't really have to do any math. You just have to interpret it. Any questions on this little printout? Because you will be seeing this a few times. But that's how you interpret it. Sometimes on the test, this will say standard error of coefficient, like that. But yeah. Did anyone have any questions on any of the chapter 21 problems, if you guys did any of them? I have one. This one, number 14. Okay. So 3 people reported the results of trials in which clouds were seeded and amount of rainfall recorded. They reported on 26 seeded and 26 unseeded clouds in order of the amount of rainfall. So in case you know what seeded means, that just means like basically people picked out a bunch of clouds in the sky and gave them numbers randomly. Like have you like seeding a bracket kind of thing? It's the same concept. Here are 2 possible tests. Basically, this is asking, is this a paired test or a 2-sample test? AKA, is there a natural pairing between the seeded and the unseeded clouds? Assume all the math parts right. What do you guys think? So they basically took a bunch of clouds in the sky and they gave them numbers, and they compared them to a bunch of clouds in the sky that they didn't give numbers. Is that a good pairing? Is that a consistent good pairing or not? Raise your hands if you think it is a good pairing. Okay, raise your hands if you think it's not a good pairing. Yeah, it's not a good pairing. They're just choosing clouds at random. So in this case, you'd use the 2-sample test. And using that p-value, would you reject or fail to reject the null hypothesis that the mean of the differences is 0? Based on this bottom p-value. Yeah.
The reason that's Like the pairing because of no different, there's no difference between a cloud that I see in the cloud.
Yeah, it has to be like systematic and consistent. So they're literally just picking random clouds in the sky and saying, oh, we're matching these together. You know, it'd be like if I just paired you with someone else in the room and someone with someone else and like compared all your quiz grades or something, right? There's no rhyme or reason to it. That's why you need a consistent, like husband, wives, or brother and sisters, or pets within the same household, stuff like that. So it's consistent and it can be replicated evenly, and there's no ambiguity about what the pairing is. But so what do you conclude with the p-value? The p-value on the bottom for the two sample tests. Reject or fail to reject. Let's assume alpha is 0.05. I heard fail to reject, right? 0.0538, 5.4% is bigger than 5%. So you fail to reject the null hypothesis. Any questions on this one? Here's another one. This one, number 13 on the left side. Value for labor force participation rate of women is published by the US Bureau of Labor Statistics. They're interested to see if there's a difference in female participation between 4 years. They check randomly selected cities. So, is this a natural pairing? They're comparing the values in one city with itself another point in time. So taking values in each of these cities in 1968, then they took values in 1972, and they're comparing the difference across years. Is that a good pairing? Yeah, that's like the best kind of pairing, because it's very clear what you're comparing to. You're comparing to yourself at an earlier point in time. So then you'd use the top test, right? You'd use the pair test. Now you can write it like how they do, or just write mu sub d for difference. But yeah. And in terms of the math, just it functions exactly like the one sample t-test that we did, was it a few weeks ago? But the important part is just that there is a pairing. If there's not a pairing, you have to do a two sample. If there is a pairing, you can do this, which is easier. Any questions on this stuff? Because that's really all there is to it. Yeah.
So for like on the test, it would be a question with two things and we would decide if we could pair them or not.
Yeah, so How's gonna look in the test. He's actually gonna narrow it down for you. So like there's a question that's gonna have some means and stuff, and it's gonna say, is it a one sample t-test, a two sample t-test, or a paired mean test? You can automatically rule out one or two sample. If there, if there's one sample, you cross out one sample. And the pair, you have to say, is there a consistent natural pairing that you can make? And that's the difference between a two sample and a pair. Yeah. Yeah. But of course, like the difference between number 13, number 14 is that 13 has a very clear pairing, right? It's cities at different points in time. But 14 is just literally picking random clouds in the sky. That you can't do that. So does that answer your question?
Yeah.
Okay. I'm gonna give you guys a flow chart that I made in office hours too, after we do chapter 22. Are we good on this stuff? Because the math will function again. This is just the one sample t-test again. Just like the sample size of the first one equals the sample size of the second equals the sample size of the difference, because you have to have n pairs. So. And you could always use the chapter 2 formulas. After you like subtract all the data, like how statisticians do it is, you add them all up, divide by n, and you do the chapter 2 standard deviation formula to get this data in the first place. On the test, it'll be given to you, just like, you'll be given the mean of differences is 2.4, the standard deviations, whatever. But chapter 22 is very different. This is going to be chi-square tests. Now, I write chi like kind of a squiggly capital letter X squared test. These are for categories. These are the only hypothesis tests that are for categories and not quantitative data. So there's going to be analogous things between this and everything I've done before, but it's kind of different. There are 3 chi-square tests. They all have the same exact math. The only difference is the hypotheses and then your conclusion. You're going to do all the math the same way. You're going to find the p-value the same way. It's just the context. So, well, first, one thing I want to point out, the chi-square distribution is right skewed. It is the only one we've worked with so far that is not symmetrical. That picture looks kind of symmetrical. So you will only be, the p-value is only the right tail. For the purposes of this class, at least. There's no one-sided or two-sided alternative. Every alternative is actually going to be a not equals 2 sign. Every single one. But in terms of the chi-square table, it's just going to be the right tail. Because it's skewed. So, there's 3 types. The first is called goodness of fit. We are comparing a sample with a known distribution. Sometimes it's also called an assumed model. Common examples are like manufacturers setting out certain proportions of like, the example I keep using is like what percentage of each bag of M&Ms should be red, green, blue, whatever, stuff like that. Or if we know things follow a certain chart. You're comparing a sample with a known distribution. The example they give is about astrological signs and the number of CEOs per zodiac sign with an assumed model. So you know you have something that you think exists. You have a model that for one reason or another you know exists. And then you have a sample and you want to see if the sample conforms to the known distribution. AKA, if in terms of like a real life purpose, maybe it's like quality assurance. Someone picks out a random bag of M&Ms, they want to see if the right proportion of colors is followed. Stuff like that. That's goodness of fit. Goodness of fit has one variable. It's important. There's one variable, but a bunch of categories for that variable. We're gonna get to the math in a minute. I just want to explain this all to you guys first. The next is what's called homogeneity. Again, homo is Latin for same. Homogeneity is, how do they word it? You're checking to see if the distribution of a variable among all categories is the same. So like an example I keep using is like something that you'd think wouldn't be the same is like drowning across all 4 seasons. You'd expect there to be more in like the summer than the winter, but maybe like you want to see if like birth rates are the same across all 4 seasons, or maybe you want to see if like test grades are the same, or if like seasonal affective disorder is a thing. But you're trying to see if the distribution is the same among all categories. And when you do the math, we'll see that it works out that they look the same. We're gonna do the math last because the math is the same for all of them. This is again one variable. And the last one is independence. This is two variables. It is the only one with two variables, which is important because one of the biggest challenges, especially for today's quiz, for the test on Monday, for the final, is especially for the final, we're going to learn two more hypothesis tests. It's just picking out which thing are you doing. So, automatically you see two variables in a chi-square, that's independence. Well, you want to check if there is an association between the variables or not. AKA, are they independent or not? Now, for all you bio majors, you've probably done some chi-square tests before because it's pretty useful. So you're checking if there's an association between the variables or not. Of course, no association means independent. So an association means dependent. In bio, it's like for checking if genes are independent or something like that. Yeah. Nope. For the next test, yes. Yeah. For the final, no. Yeah. But the big thing for a chi-square is you should be able to tell if it's categories or not, right? So that's what makes it easy. I'm just gonna write out the math and then the best way to do this is some problems. I just wanna, it's all subtle, right? The math is gonna be the exact same no matter what, which is kind of confusing. But all it is we're just, the context is what separates each of them. Are we comparing with a known model? Are we trying to see if the distribution is the same among all categories? Maybe it's like amount of people with certain disease among different cities to see if, maybe it's like toxic chemicals in one city that give people cancer or something. I don't know. And independence is we have two variables that are categories and we're trying to see, are they related or not? Which, that especially has a lot of real world applications in like bio. So, any questions? So our conditions are counted data. This just literally means, are we working with categories or not? So this is just a yes or no. Right, if it's not counted data, you're not doing this. We have independence, which is the same it always is. Simple random sample or whatever. And then we have the equivalent of the success failure condition, the nearly normal. It's called expected cell count. And this is the one that requires the most work. Each cell is at least 5. Now, expected cell count is going to be the majority of the work for a chi-square problem, which we'll get to in a minute. Degrees of freedom, there's two ways of calculating it. If there's no table, degrees of freedom is number of categories minus 1. So if there's, 7 colors of M&Ms, then 7 minus 1 is 6. If there is a table, it is number of rows minus 1 times number of columns minus 1. Please don't mess up this calculation. Easy points. So degrees of freedom for the sake of a test are usually not going to be higher than like 4. Because then especially for a table, there's a lot of calculations. And then the expected cell count, there's two ways to do it. If no table, it is your sample size n times, I don't want to write this. It's n times the proportion. So like, if you have, let's say you assume there is 20% red, 40% blue, 40% green of something. And you have n is 50. Then the expected value of red is 50 times 0.2, which is 10. Expected value of blue is 50 times 0.4, that's 20. And expected value of green is 50 times 0.4, which is also 20. And that adds back up the sample size. So I mean, it's just n times p for some proportion, if there's not a table. And this information would be in the question. Yeah.
That a good check for it, like,
Yeah.
add them all up after.
Yeah.
Even for like the other one, like the table.
Well, what we saw in like the one in offstars was they added up to the row totals. Remember that for that first one?
Okay.
Yeah. So I'm gonna probably go over that question again because that was a good one. If we have a table, say we have a table that looks like this. What do I call this? The subscript is row, comma, column. So you're always gonna have totals. So I'm just gonna call it row total 1, row total 2, row total 3. This down here is gonna be the overall total. And here we have the column 1 and column 2 total. So the expected value for x11, that top left, is gonna be the row total times the column total over the overall total. So for this value, it's this number times this number divided by this number. The denominator is always gonna be the same. For like the expected value of 3, 2 is gonna be the row total for the third column, second column total over the overall total. You guys see what I mean? So you kind of go for each data point, you go out to the row and the column total, you multiply those together, you divide by the overall total. And for this 2x3 table, you'd have 6 expected cell counts. This is the majority of the work though, for a chi-square. That's why you're not gonna have tables too big, because then, a 3x3 is just 9 calculations and stuff. It's just more of the same thing over and over again. Any questions on this formula? So for any data point, it's that row total times that column total divided by the overall total. And those are the two ways. Tables are only for homogeneity and independence. There's not going to be a table for goodness of fit. So that's another way to rule out which one you're doing. Yeah, tables are only for homogeneity and independence. And then we have our chi-square statistic. It is the sum over all cells of observed minus expected squared over expected. Usually it's written, and how I wrote it on my notes is OBS minus EXP squared over expected. This is how your book writes it. Your expected values come from the calculations and your observed is your data. That's why the expected cell count thing is so important. That's where you're getting all your expected values. And then you go to the chi-square table and you find your p-value, which we'll talk about in a second. But this is the chi-square statistic. So in this thing above, we have 6 cells, so there should be 6 things added together. In the one on the left, there's 3 categories, so you should be adding 3 things together. Any questions? And then just looking at the chi-square table, it's quite simple to use. You go to your degrees of freedom, you go across, and then you go up for your p-value. Same rules, like let's say we have degrees of freedom 3, we have a number that's over here, right? Like 8.3. Then our p-value is going to be between these. If you have a value over here, our p-value is less than that. If we have a value over here, our p-value is greater than that. Oh, that's another way to do it. You could always just write, I didn't realize that. You could always just write a greater than sign in p, and that gives you your thing. It always works. Yeah. So yeah, it's the same rules as the t-table in terms of like the inequality. But yeah, you just go to your degrees of freedom, you go across. And then you write reject or fail to reject, and you move on. So that's what it is in a nutshell. Now we'll do some examples. I wasn't really a fan of which questions were chosen for your homework. So yeah, we have time. Okay, we're gonna look at number 5. So it starts in the bottom left. An analyst at a local bank wonders if the age distribution of customers coming for services at his branch in town is the same as the branch located near the mall. Now, just from that one sentence alone, the fact that we're asking if 2 distributions are the same means homogeneity. Do you guys see that? Because going to the definition, checking to see if distribution is the same among all categories. Word same gives away. He selects 100 transactions and makes a table. Notice how there's only one variable in this table in the top right. That variable is age, or age groups. And it's distributed among 2 locations. That's another way you can see its homogeneity. And if you look at the expected cell counts, right, you have to do column total times row total over this, right? 50 times 100 over 200 is 25. So if we make, you kind of just want to make a second table. So this is 25, but also the one below it is 50 times 100 over 200. That's also 25. The middle, 90 times 100 over 200 is 45. Same for this. And this is 30 and 30. So for a homogeneity, the rows, the expected distribution of the rows is the same. Which makes sense because we're trying to see if they're the same. We're going to assume they're the same. So our expected cell count, our expected cell distribution is distributed across the two towns is the same. You guys see what I mean? This will always be the case for homogeneity. That it'll be because this is the expected table. This will always be either the rows or the columns, depending on the scenario. Distributed across the variable, which is, in this case, age, will be the same. And the chi-square statistic would be 20, this top left number. Here it is. It'd be 20 minus 25 over 25 squared. Nope, just the numerator. Because this is our expected. Plus, then we could just go down. 30 minus 25 squared over 25. Plus 40 minus 45 squared over 45. Plus 50 minus 45 squared over 45. Plus 40 minus 30 squared over 30. Plus 20 minus 30 squared over 30. You match each number in the original with the new expected cell. And there's 6 cells, so you have to do it 6 times. You plug that into a calculator, you'll get your chi-square value. Any questions on this? Yeah.
How do you get numbers, you know, thinking if
So for the top left, I'll go through. So we're looking at this 20, right? So the column, the row total is 100. The column total is 100. The overall total is 200. So I do it over here. Row times column over total. And then you go, the one below it is actually the same numbers, right? And then for 40, it'd be 90 times 100 over 200. And the one below it would be 90 times 100 over 200. And then the third is 60 times 100 over 200, 60 times, yeah. So if you have a table, always just make a second table in the same orientation. And then, because then for the chi-square statistic at the bottom, you just match it up. And there's a little difference when you write the hypotheses. You want to write them in sentences and not with math. For goodness of fit, you want to say like, that's where I would say it. Like the assumed distribution is the same as the population distribution. The alternative is not. You just add the word not into the previous sentence, which I want to rewrite. For homogeneity, because same means equal. So there's an implicit equal sign there, just like there always is. The null hypothesis is that the variable is distributed the same among all categories. And there's actually 2 ways you can either write is not, or at least one category is different. If just one category is different, you reject the null hypothesis. And then independence either the two variables are independent slash not associated, and then dependent slash associated. So all of them, the null hypothesis has an implicit equal sign, and the alternative has an implicit not equal sign. But there's no two-sided alternative. It's just always one-sided. On your test, don't just write is not like I did, like write out the whole sentence, but just the exact same sentence and you just add the word not, is not the same or whatever. Yeah. Mm-hmm. Mm-hmm. Like this? Like this stuff? This is a times. Yeah. This is just me like putting some subscripts. But yeah. 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 There's this again if you need it. I'll do an example in a minute. And I'll make you guys a flow chart of just how to decide which tests. The good news is the quiz today is going to be basically what you're going to see on Monday. Just the same style of question. Everyone go with this? Can I move on? Okay. Oh yeah, let's finish up this. So you plug this into a calculator, you get your chi-square value. Notice how, well, what's the degrees of freedom for this table? It's row column -1 times column total -1. Try again. 2. There's 2 rows. There's 3 columns. It's 1 times 2. Yeah, please don't get that wrong. The quiz or test. Row total time -1 times column total -1. You're really never going to be working something bigger than like 4 for the purpose of a test. And rejecting, failing to reject is the same as always. Okay. In office hours, we did the math for 9, not 10, right? For the people who are in office hours. Okay, so we'll do 10. All right. So look at number 10 over here. So this is talking about the epic poem, the Iliad. Injury sites and weapons. How many variables are there? 1 or 2? 2, right? Injury site is 1, weapon is another. So we're going to just do this whole hypothesis test, just to give you an example of what this looks like. There's 2 variables, injury site and weapon. Everyone see that? So our null hypothesis is going to be injury site and weapon type are independent. And then the alternative is that they are dependent. Our conditions, counted data. Is this categorical? Obviously, yes. Are they independent? Probably. Expected cell count, you're gonna have to do all the math and then come back to this. Because there's no way you can tell by just looking at it. Before we do that, what's the degrees of freedom? Yes, 4. All right, so you want to make another table. And now you guys are gonna plug a bunch of numbers into your calculator. So for the top left number, it should be 12 times 67 over 145. And so on. The expected cell count is that each cell is bigger than 5. Or it can be equal to 5. Bigger than or equal to 5. They're gonna have to do, in this case, 9 calculations. Which is why you're probably not gonna have something even this big on your test. A 2x3, like the previous example, is probably the biggest you got. Even though the numbers inside are really small numbers, the expected count could just be higher. Way that this would be a homogeneity table is, let's say the columns were like different locations or different genders or different age groups. Then you're seeing if a variable is distributed over those groups, and that'd be homogeneity. If like weapon was replaced by age, gender, battle site, year even. Yeah, the majority of the work is right now doing these expected cell counts. And since it's not homogeneity, it won't be the same numbers over and over again. Anyone need help calculating them? For each value, you go out to the row and column total, and multiply them and divide by 1. Everything's divided by 145 in this case. The overall total. Table total. Like the very middle number should be 45 times 11 over 145. That's not good. I mean, your math might be fine, but yeah, it's gonna violate it. Anyone have the 9 numbers per chance? Yeah. Yeah. So you're going row by row? Okay. 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 Okay, so a bunch of these, so it actually fails the expected cell count condition. We'll still do the math for the rest of it. But yeah, that's not good. So the any questions on how she got those numbers? Yeah. Yeah, so this one right here, the one that's a 1. Is gonna be 67 times 11 over 145. Row column total times row total over total. And chi-square is the sum. In this case, it's gonna be 9 things. All cells of observed minus expected squared over expected. And just so you guys get the practice, I'm gonna make you do this all on your calculator. So I'll set up like 2 terms. So the first term would be the observed of 5 minus the expected 5.54 squared over 5.54. The one that's a 2 on the table would be 2 minus 3.72 squared over 3.72. And you just keep doing that 9 times.
Corresponding square.
Yes, so you match up the squares. That's why it's good to, so like the 5 in the top left corner matches up with 5.54. The 5 in the very middle matches up with 3.41 and stuff. The 61 matches up with 56.37. It's the things in the same coordinate. Observe. Oh. Let me just. So it's sum over all cells, which in this case is 9 of observed minus expected squared over expected. So unfortunately, if you mess up your math on the expected, you're going to get the chi-square wrong. And potentially the expected cell count wrong. Now, if you add up each of the rows, they will add up to the row total. If you add up, and if you add it up by the rows or the columns, they will add back up to the row and column totals also. So that's one way to check yourself. You don't have to do that, but if you just go across the row, the top row, it'll add back up to 12. The first column will add back up to 67, and so on. The total of all 9 numbers will be 145. Yeah. The what? So this thing right here, that's chi-square, is the test statistic. It's a test statistic of all 3 chi-square tests. That's what I'm saying. The math, the assumptions, and all the math is the exact same. It doesn't even matter what your hypotheses are necessarily. But it's just the one thing that separates them is just the context. This is an independence test because we have 2 variables. So the p-value in context is the probability of getting this chi-square value for an independence test, assuming that the 2 are independent. One way you can kind of eyeball if you're gonna get a big chi-square value is just if the expected numbers are much different than the observed numbers. But chi-square value is usually not gonna be bigger than like 20. These will be numbers bigger than 1 usually, but they can be fractions. They can also be in the hundreds or thousands potentially. Anyone get a chi-square value yet, by any chance? Yeah, everyone, it's worth just doing your calculator once, just because you'll have like you're gonna have more than 1 chi-square test next week. And you're gonna have one on your quiz in a few minutes. What's up? Yeah.
You said it failed with the expected count.
Yeah.
And that was that they're all under or equal to 5.
Yes.
So there's a way to like kind of eyeball that if it's crazy skewed.
No, you kind of gotta do the math.
Oh, like expect. I don't know.
'Cause
I don't mean
like
what
the
you
one
mean.
that was the one in this table, right?
Yeah.
Had actually that cell passed the count, you know, but it was the ones like,
But like.
yeah,
one,
so you
two,
can't. I guess you could kind of eyeball it based on the totals, but
that's like-
yeah, I mean, yeah, you can kind of eyeball it. Yeah. But you have to do the expected cell counts for the rest of the test anyway. It's like, yeah. Yeah, Michael.
Well, so
Well, like you shouldn't do it, but I just want to, you know, give you guys the practice. So we're still doing it anyway. But if it fails on the test, he won't tell you to do the rest of the question. That's fair. Yeah, that's a fair way of eyeballing it. Yeah, if it adds up to 12, then not all of them can be at least 5. Yeah, that works. Still do the like a question would probably say, what test is it? State the null and alternative hypotheses, assumptions, you say it fails, and then it'll say do the expected cell counts anyway, just so you can prove that it fails. Because yeah, not everyone's gonna know the eyeballing trick and stuff. And just so we know that you know how to do this calculation. But in the textbook, they never give you an alpha level and they never ask you to do the assumptions. But yeah, so 10.453, let's just assume the assumptions work just to finish the test. So degrees of freedom 4. 10.453 is in between these two, right? So the p-value is in between 0.025 and 0.05. If alpha's 0.05, we reject. If alpha is, let's say, 0.01, we fail to reject. But, you know, depending on the question. But that's basically what a chi-square test looks like. You do the assumptions, you have your conditions. The expected cell count is the biggest part of it. Did everyone agree with that 10.453 for whoever used the calculator? And did you guys get that? If you guys didn't get that, you might want to check. I mean, at the end of the day, it's just a bunch of, you know, subtracting and multiplying, dividing. Any questions on this stuff before your quiz? Anything else? We all good? Okay.